Hi, everybody. So we're going to talk about the integral test in this one. I'm going to start by giving us a little bit of, well, I hope a little bit of intuition on it. And then I'm not going to prove it necessarily, but we'll go through some work that I think will help us at least believe it. And then we'll do a couple of examples. So let's see. Let me share something with you. So I want to take a look. We're going to start by looking at the sequence. What are we going to look at? The series, excuse me. We're going to look at the series n equals 1 to infinity of 1 over n squared. Okay? So let me actually share something else with you. Let's start by looking at a graph. Where are you? All right. So first of all, what I've done here, what I'm looking at here, let me write on this a little bit. These are boxes representing our sequence, right? Or rather, I should say, the area under these boxes represents our the sum of the series. Right, so let's write this out. We've got a series, n equals 1 to infinity of 1 over n squared. Right, so let's just write out what this would look like. We've got 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and on and on and on. Right. Well, if you look at these boxes, these rectangles, each one has a width of 1, and the height is going to be these values. The first one goes up to 1, the second one goes up to 1/4, 0.25, the third one goes up to 1/9, 0.11, a 16th, a 25th, and so on, right? So the area is going to be 1 times those values. So if we added up all this area, all the area of these rectangles, we would get the sum of this series. Well, that maybe gives you an idea of why we're calling this integral test, because let's compare this. Here's a graph of the function. This is the function y equals 1 over x squared for x greater than 1, right? So what we notice, right, let me do one more thing here. What we might notice is that the area under this graph from 1 to infinity is more than the area of all these rectangles except for this first one. Right, so this first one I'm leaving outside of it, but if I look at the rest, of these rectangles, they're below the area under this curve. So in other words, what I'm going to claim is the following. I claim that my series from n equals 1 to infinity of 1 over n squared is less than 1 plus the integral from 1 to infinity of 1 over x squared dx. Right, the 1 is just to account for this thing right here, so this is the first term. The rest of them are less than this integral from the picture. Right, we can go through a little proof of that, but it's pretty easy to show that this is a decreasing function. We're equal to the function on the right hand of each interval, so we have to be below it everywhere in the interval. It's probably easier to prove if you have less than or equal to. It won't really change anything about what we're about to do. But all I want to convince you of right now is that the sum, if this sum exists, should be less than this, right? Now, if this integral turns out to be infinite, that's not really telling me anything. And it's actually kind of a nonsense statement. Maybe I should put that in there for that eventuality. That if I know that I'm less than something that turns out to be infinite, I could also be infinite. It's just sort of saying that at each step of the way, I'm below it, but if they're both going to infinity, that could be perfectly reasonable. So let's now compute this integral over here and see what happens. So let's switch to my paper. Give me 1 second here. Let's go to, all right. So remember what we had just done. I hope convinced you that this integral, or this series here, if it has a sum, should be less than this expression on the right. And so let's now just take a look at this integral. So we want to take the integral from 1 to infinity. Let's write it as x to the -2 dx. Remember our definition for these improper integrals. We take the limit as t goes to infinity of the integral from 1 to t, x to the -2 dx, which is the limit as t goes to infinity of, well, let's see, the antiderivative of this is -x to the -1. And we're evaluating this from 1 to t, which is going to look like the limit as t goes to infinity of, let's see, -t to the -1 minus a minus, so I'll get a +1 to the -1. Let's see, as t goes to infinity, -t to the -1 goes to 0. Remember, this is 1 over t or -1 over t, doesn't matter, it still goes to 0. All that's left is this 1 to the -1, which is of course just 1. So this whole thing is equal to 1, right? Which means up here, this whole thing is equal to 2. So in other words, what I've just shown, n equals 1 to infinity, 1 over n squared, is less than or equal to 2, okay? Now, notice we also know, for instance, that this thing, 1 over n squared, is also positive, right? I think that's pretty obvious. We're starting with positive numbers and adding positive numbers. And so from these two things, we can also prove pretty quickly that n squared is decreasing as the denominator gets bigger. It's decreasing, so that means it's a monotonic and bounded sequence, which we know converges, right? So that's really what we've determined here, which means that we know the sequence converges, right? And this is what the heart of this integral test is. Just for curiosity's sake, it turns out this sum is, I believe this thing sums to pi squared over 6, it turns out. People have proven this. I do not remember how that proof goes, but it's a fairly famous problem. The book might even have it, but you can certainly find that proof out there. Which makes sense. Pi squared over 6 is, I mean, it doesn't make sense that it turns out to be such a regular number, but it certainly fits within our range, right? Pi squared is going to be what, like about 10. So 10 divided by 6 is certainly between 0 and 2. So at least it fits our estimate there, okay? So in any event, that's the big idea of, or at least half of the integral test, okay? Let's go back to that graph for a second and look at the other side of the integral test, okay? So let me close the one we were just looking at, and let's look, for instance, at a slightly different series. So here, I'm now considering the series, oh, let me turn this grid off to make it easier to see. Let's consider the series, oops, I want to keep those on and that off. Now I'm looking at the series 1 over the square root of n. Right, so now I'm using this graph to illustrate something about, oops, 1 over the square root of n for n equals 1 to infinity. right? So here, right, I did the same thing. I created these boxes whose areas are representing these terms, right? Something like 1 plus 1 over the square root of 2 plus 1 over the square root of 3, and so on, right? And then I'm comparing that thing to the graph of y equals 1 over the square root of x. That's what this blue line is, right? And we noticed that the area, if we looked at the integral, here, let me write this, my series has to be greater than or equal to the integral from 1 to infinity of 1 over the square root of x dx, right? That's what this picture is showing us. The areas of these rectangles are above this graph. Well, I'm not going to prove this one for you. It'll be good practice for you guys to remember how to do these improper integrals. But this turns out to diverge to infinity, okay? So what I just wrote here is nonsense. This is not equal to infinity. Let's be more careful. What I should say is the limit as t goes to infinity, 1 to t, 1 over the square root of x dx is equal to infinity, right? Meaning that the area gets larger and larger and larger without bounds, so it never stops, which means these things, these rectangles which are above it, must also get larger and larger and larger, and so this series will diverge. And that's the other half of the integral test, right? The idea is we're comparing these series to functions that have the same values again on the integers. So let's write out our integral test now in detail. Give me a second to get to the right place. Let's see. All right. So our integral test can be written as, let's see, we want to say, we're going to start with a continuous function f. So let's say, suppose f is a continuous positive and decreasing function on the interval 1 to infinity, and let a sub n equal f of n, right? Where n is in the set. Let's just leave it as written. I don't need all this extra stuff. Okay, so what we're basically doing is saying we have a function and then we can define a sequence based on the values of the function at each of the integers, right? So if you go back to those examples I just gave, in each case, the sequence and the function were equivalent if you plugged an integer into the function. Okay, so if we have that situation, if that's true, then the series n equals 1 to infinity, a sub n is convergent if and only if the integral 1 to infinity of f of x dx converges or is convergent. Okay. So in other words, they diverge or converge together. The if and only if actually means it goes in both directions. But we're really only going to use it one way. We start with a series. We want to see if it converges or diverges. So we look at the integral of the function that has, as long as it has the properties that are listed up here, then we look at the convergence or divergence of that integral, right? Just to be clear, I want to note that we're using the word convergent differently here, right? They're pretty well related, but we actually mean two different things. Convergence of a series means the limit of partial sums converges to a number. Convergence of an integral means that expression, the limit as t goes to infinity of 1 to t of f of x dx, that has a limit, right? And those are two different things, right? They're very related, but they are two different things. So from context, this convergence is referring to an integral. This convergence is referring to a series. But this whole test connects those two things, right? So just to make it perfectly plain, what we can say is if the integral from 1 to infinity f of x dx converges, then the series converges. And if the integral from 1 to infinity of f of x dx diverges, then the series diverges. Okay, so that's already up there. I just want to make it perfectly clear what this is. So this is another great test for us, right? Because we know how to handle integrals, and so, or at least some of them. And so if it turns out that that's available to us, we can use it. So let's do one more example. Yeah, let's just do one more and call it a day on this one. So I want to look at, this is a series that I showed you in another video, in our test for divergence video. I want to look at the series. Let's see, the sum from 1 to infinity, n equals 1 to infinity of n squared over e to the n cubed. Okay. Now, if you remember, we noted in an earlier video that n squared over e to the n cubed goes to 0 as n goes to infinity, right? This means the test for divergence is inconclusive, right? Remember, the test for divergence can only tell us that something does diverge if this limit is not 0. When it is 0, it could still diverge, it could still converge. So we have to try something else, right? And this is going to be how these problems go sometimes. You try a test, that test is inconclusive, so you try another test, right? There are a few of these out there where this kind of thing can happen. All right, so what do we need in order to use the integral test? So let's start with this. I have f of x equals x squared over e to the x cubed, okay? So this is clearly a function equal to this series, equal to the terms of this series, equal to the sequence of terms on the integers, right? If I plug in an integer, I get that. So that was, remember, one of the conditions I need. I also need to know that it's positive and decreasing. So positive is easy. X squared is going to be positive is always going to be positive, unless x is 0, but we only care, remember, about from 1 to infinity. And exponentials are always positive. So it's positive. We got to see that it's decreasing. And the only way I know to check that, the easiest way I can think of to check that, is to look at the derivative. This is a good opportunity to practice derivatives. So f prime of x, I've got to use the quotient rule. The derivative of the top is 2x. I leave the bottom alone, the denominator. Then I take the derivative, let's write our x squared, and the derivative of the denominator is going to be, well, it's a chain rule where I take the derivative of the exponential, and the chain rule makes, we take the derivative of this exponent here. And all of this is divided by the denominator squared. E to the x cubed squared. Right. Let's do a little bit of algebra. In the numerator, I can factor out, let's see, I can factor out an x, and an e to the x cubed. So I'll have x e to the x cubed. And what's left here? I have a 2 minus what's left here. I've got a 3. I have 3 factors of x left. Right? And then I've got in the denominator e to the 2x squared. Okay? So there's my derivative. Remember what I'm trying to show. I want to show that this thing's decreasing, which means its derivative should be negative. So let's just start thinking about the sign of this thing. The denominator is always positive. It's an exponential. This thing's always positive. It's an exponential. X is going to be positive because remember, we're only looking from 1 to infinity, right? That's the conditions when x is 1 to infinity. So x is always positive. So the only thing that can tell if this thing is positive or negative is this thing, right? So we want to know when is 2 minus 3x cubed less than 0, which is the same as saying when is 2 less than 3x cubed, or when is 2/3 less than x cubed, or when is the cube root of 2/3 less than x, right? Well, this is just saying, let's just write it in a nicer way. This is true. In other words, the derivative is negative whenever x is greater than the cube root of 2/3. The cube root of 2/3 is less than 1, right? It has to be a number smaller than 1. So what I now know is that whenever x is greater than, here's 1, some number smaller than 1, all these x values in that direction, my derivative's negative. In other words, my function's decreasing. So that means we've satisfied the conditions. Where did you go? We've satisfied the conditions that we have a positive decreasing function on this interval, and it's equal to our series, right? Okay, so now we're ready to compute the test. So what I'm going to do now is take the integral of this function from 1 to infinity, okay? So let me write that out. The integral from 1 to infinity of, let's see, it'll be, let me write it a little bit simpler, x squared e to the negative x cubed dx, right? Instead of having to have a fraction, it's just a little nicer to have it written this way, right? So we get the limit. Actually, let's do the limit afterwards. Let's do the integral by itself first and then come back and do this. So I want to look at x squared e to the negative x cubed dx, forgetting about the limits of integration. I just want to take an antiderivative. And you might notice that we can use a u substitution on this integral. So if I use u equals x cubed, then du is 3x squared, or dx, and 1/3 du equals x squared dx. So putting those substitutions in, we will have 1/3, what do we have? We've got 1/3 du replacing x squared dx, and we'll have e to the negative u du. The antiderivative is negative 1/3 e to the negative u plus c, or negative 1/3 e to the negative x cubed plus c. Okay, so there's our antiderivative. Now let's take the integral from 1 to infinity, x squared e to the negative x cubed dx equals the limit as t goes to infinity of 1 to t, x squared e to the negative x cubed dx equals the limit as t goes to infinity. So I've already got my antiderivative here. It'll be negative 1/3 e to the negative t cubed plus 1/3 e to the negative, and I'm putting in 1 for x, so just 1. Right, so what does this all look like? Well, here, taking the limit as t goes to infinity, a negative exponential. As t gets larger, this exponent gets larger, it's all going into the denominator. This thing disappears and goes to 0, and this thing looks like 1 over 3e, right? E to the negative 1 just puts it in the denominator. Okay? So let's finish this up. What we just did, we found f, a positive decreasing function on this interval that is equal to our series on the integers. And we found that the integral of this function over the interval 1 to infinity converges. Therefore, our series converges. So we can say the series n equals 1 to infinity of n squared over e to the n cubed converges, right? It does not tell us what it converges to, but it tells us that it converges. All right? All right, so that was a pretty long one. We did some shorter ones earlier, but it's a pretty good one. And that will be it for this video. See you next time.